Hello. In this experiment, we attempted to find the relationship between acoustic absorptivity and sound density by recording the acceleration response of a material when it is hit with a low-frequency sound played by a bass amplifier. This experiment was performed by Xander Fioretti, Michael Ruse, Konrad Kremsner, Christopher Strilowich, and myself, William Vargas.
Hello, my name is Michael Roos, and I will be doing the background portion of the ME 401 project, Correlation Between Density and Acoustic Absorptivity. To begin with our introduction, our experiment, Correlation Between Density and Acoustic Absorptivity, aimed to establish a relationship between density and acoustic absorptivity of a material by tracking how it reacts to the input of a loud frequency sound. This was done by using a bass amp and an accelerometer to document response frequency and amplitude. If this method is successful, it could provide a more affordable method of acoustic testing for consumers. Conventional methods of acoustic testing call for the usage of specifically designed reverberation room or chamber technology for measurement of sound absorptivity of different materials across various frequencies. For what is new and different about our approach, during our research, our team found little data referring to oscilloscope testing for basic materials, so it was theorized that our approach method of testing might reveal new information that could be applied to real architectural design and testing. The significance of our project research matters because testing the acoustics of densities and different commonly used building materials could yield new information. Our hope was that results would yield new insights about structural stability and how to better engineer acoustics in basic floor plans and how to find better ways to conduct research. The key question of our test was to see if we could discover new data regarding affordable material acoustic testing and if we could apply that knowledge to engineer realistic improvements for structures. The test objective was to collect new acoustic data about several common building materials, mainly using oscilloscope and proper lab setup after conducting ample research and preparation. Our team theorized that there would be noticeable differences in factors with our output data before we began testing, and as will be stated later, we did not find this to be the case. For our simulation, assumptions were made before testing began, including several factors about the environmental factors of the testing room. Several control parameters were set up before testing began to assure that the only variable would be the changing of materials. That's the end of the background portion. Thank you.
The experimental test plan consists of hanging samples of material in front of an amplifier, then playing specific frequencies over the amplifier, recording how the sample moves. The experimental diagram shows the test material hung from a nylon string clamped to a tabletop. The test material has an accelerometer attached to the back of it at the centroid of the material. The accelerometer is attached to a signal conditioner, which in turn is attached to an oscilloscope. The amplifier is placed in front of the test material and attached to a laptop via an adapter. The ambient sound, temperature, and pressure were kept constant during testing. The accelerometer was dropped and its acceleration was calculated and compared to its gravitational acceleration constant to ensure the system was calibrated. Once data was collected, the acoustic absorptivity constant of each material was calculated and compared to the material's density in search of a trend between the two properties. The test procedure consisted of turning on the oscilloscope, signal conditioner, and speaker and amplifier on. Once this next step was to wait for the test sample to stop moving. The next step was to play the frequency over the amplifier. Then the frequency and amplitude of materials displacement was recorded from the oscilloscope. Then the speaker was turned off. Steps 2 and 4 were repeated for all test frequencies. And then steps 2 and 5 were repeated until until every test frequency had been played. Then the test sample was replaced with a new material test sample, and steps 2 through 7 were repeated until all material samples were tested. And then the acoustic absorptivity constant was calculated from the data of each material. There was potential risk for hearing damage, but that was mitigated with in-ear hearing protection.
Hi, my name is Xander Fioretti. I will be talking about the results we got from our experiment. Primarily, the results that we got were inconclusive. We couldn't find a correlation between acoustic absorptivity and density of a material. The data we got is down below. We got the data from an accelerometer and oscilloscope where we measured the frequency that material was vibrating when it was exposed to a frequency that we produced. The X1 and Y1 values are all values that we got from zooming into the oscilloscope and finding different points for each wave that was produced. We then turned that into a period and thus frequency and amplitude, and we used the frequency divided by the density to find the acoustic absorptivity, which would be the frequency per unit of density. So it also normalizes the curve that you see on the graph up top. So the data that we got was very interesting. As you could see, plywood, which seemed to have the mid-tier density, had the highest acoustic absorptivity out of all three samples, while steel, which had the highest density, had the lowest acoustic absorptivity. So that really leaves us to not have any conclusions we could really draw from the densities. However, if we still were able to find linear trends between all the data, we would be able to come up with a equation that would be able to model any kind of density. But unfortunately, the data that we got for plywood and drywall seemed to be more parabolic than linear. So we were not able to find a reasonable equation to use for the for density and acoustic absorptivity. We used some very precise instruments. The oscilloscope and the accelerometer are both extremely precise when taking measurements. So the uncertainty that we got from this experiment was extremely low. So our claim that there is no correlation could be thoroughly supported through this data and the uncertainty. Thank you.
In conclusion, our hypothesis for this project is that there's a correlation between a material's density and its acoustic absorptivity. After conducting the experiment and analyzing the results, there are no observable trends. The findings suggest that nothing conclusive can be drawn, and the hypothesis is disproven. Potential errors in the outcomes or flaws in the testing methodology could have contributed to this. For the future, investigating different ways to conduct this experiment may reveal whether procedural inadequacies or an invalid hypothesis is the cause of the results.
We would like to conclude our presentation by taking some time to thank our professor, Dr. Hoover, as well as our teaching assistant, Mehdi Yazdi, for their assistance, feedback, understanding, and kindness towards everyone involved in this experiment from start to finish. Without their help, we may not have realized we were making some crucial errors towards the beginning and had to change course halfway through. We would also like to take some time to thank our members of the group and highlight some of their contributions to the project. Michael was responsible for the material acquisition, as well as writing part of the final paper, including the background and the abstract. Conrad was responsible for the equipment setup, as well as experimental testing, and working on the final paper, including the experimental method section. Christopher was responsible for part of the experimental testing, as well as the risk assessment and conclusion on the final report. I was responsible for the equipment setup, materials acquisition, experimental testing, as well as part of the viscous flow analysis that we did for our final progress report. Xander was responsible for materials acquisition, experimental testing, and the test results section of the final report. He was also responsible for writing many of our progress reports as well as the facilitation of most of the responsibilities throughout the completion of this project. Thank you for your time.